Hello, my name is Anuj Bhatia, and this is Lab 3, Black Hole in Orbit. So the introduction for the main purpose of this lab was to create two computational models in GoScript, one to simulate a star orbiting a black hole in part 1, and another to simulate a spaceship orbiting a planet in part 2. The objective of part 1 was to find the net force of the star and the mass of the black hole, and the objective of part 2 was to find an initial speed for the spaceship so that it can get in motion and orbit without crashing into the planet or its moon. Some fundamental physics principles I use were the velocity update formula and the position update formula, which would update, for example, the position of the spaceship or the star in parts 1 and 2. The gravitational force formula GMM over r squared, which is used to simulate forces from, for example, the planet on the moon or the planet on the spaceship or the black hole on the star in both of our models. And then finally, F net is equal to F perpendicular plus F parallel, and this is mainly to simulate how the forces would change in orbit because there were circular and elliptical orbits. For both parts in each iteration. Some initial conditions. In part 1, the system was a star, surroundings was a black hole, initial time was 0 seconds, change-in time was 86,400 seconds, which is equivalent to a day, and the star mass was 2.3 times 10 to the 30. For part 2, the system was a spaceship and moon, the surroundings were a planet, the planet mass was 6 times 10 to the 24th kilograms, the moon mass was 7 times 10 to the 22nd kilograms, spaceship mass was 7 times 10 to the 12th kilograms, change in time was 30 seconds, initial time was 0, and final time was 60 times 60 times 2500 seconds. So details about the computational model for part 1. So this chunk of code initializes some of the basic variables like g, the mass of the star, delta t, initial time, and then it uses indexes to calculate the x and y velocities as the loop iterates, and then moves to the next time after this data is collected for one iteration. For the next part, I created a list called MBH, which stores each black hole estimate for each iteration, and then I'll average them later to find the mass. And then we initialize a while loop. We find momentum, final momentum, initial momentum, change of momentum, dp/dt, f net as dp/dt, p hat in order to calculate f parallel and f perpendicular. And we find the estimated mass of the black hole for this iteration by rearranging the gravitational formula. And then we append this result to the list that we created earlier, and then we'll average this list later to find the mass. And we update star position and trail for our results. So for this next part of the code, we update f net, f perpendicular, and f parallel, the arrows in the final result for each iteration. And we update delta t and the index for the next iteration to find velocities and the next data set. And we find and print the average mass of the black hole from the list of mass values after the loop is over and all data is collected. So these are my results for part 1. As you can see, we have the star and orbiting the black hole, and I found the estimated black hole mass to be 8.31 times 10 to the 33rd, using the list and averaging all the values in that list. So for part 2, this first part of the code initializes the spheres and trails for the planet, ship, and moon, and then sets some of the initial conditions like planet mass and moon mass and the gravitational constant. And we calculate the moon speed using v is equal to square root gm over r, and we use this to initialize the moon velocity, and then we print the moon speed and calculate and print the period. And then this part of the code also initializes the initial speed of the spaceship. So this next part initializes the while loop and then finds delta r of the planet to the moon, r hat, and then uses f is equal to gmm over r squared times r hat to find the force of the planet on the moon. And we calculate the total net force on the moon by adding all the previously calculated forces. And then we repeat the same steps that we did for the planet on the moon to find the force of the ship on the moon, planet on the ship, and then moon on the ship, and then the net force on the ship. So this next part of the code updates the velocity and position of the moon and the spaceship, and using the velocity and position update formulas. And if the change in r of the ship is to the moon or the ship to the planet is less than the radius of the moon and planet at that moment in their orbit, we print a crash message, and then it breaks the loop. And then we update the trails using the updates earlier, and then we update delta t for the next iteration. And this was my final results for part 2. I didn't get a proper figure 8 orbit, but because that would have taken too much time for the simulation. But I did get to break out of orbit, not crash, and also just have that initial curve for figure 8. So then some possible sources of error are that we assume that there are only gravitational forces acting on the systems in both the parts, and then we assume that no other planets or other universal bodies were present in the simulations, and other calculation errors and using rough estimates could have been some source of error. There are some additional questions. For the first what does it mean question, I said that while f net is equal to dp/dt, they're different how they're observed and measured, and the force of an object is when something acts on a system, causing it to change in a way unless it's counteracted. However, a change in momentum is based on how the object's momentum vector and its speed vector change. And for the what if in part two, I said the main interaction that I would have to include in my model are the gravitational interactions between all the objects in the system, such as the black hole and the star, planet and moon, etc. And the more dominant interaction would have been between the black hole and the star because they're the closest, and the black hole also has the largest mass and exerts the largest force out of any of the other bodies on the star. And then in conclusion, using GlowScript and the law of universal gravitation, I was able to find the mass of the black hole. I was also able to estimate a velocity to launch the spaceship in an orbit around both the moon and the planet, and I was able to use key physics principles to apply and see how they affect real objects in simulation and get a deeper understanding of how gravitation and the impact forces, masses, and velocities play into it. Thank you.